very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. Now, in this lecture today, we'll try to introduce the distribution network load flow and its sparsity quantification. We'll also discuss about graphical load flow analysis with different load models, three-phase load flow for distribution unbalanced with DR penetrations, examples of load flow solutions in OpenDSS platform. Now let us start with what is sparsity quantification and specific to distribution load flow challenges. Now in any power system, active and reactive power flow from the generating station to load through different network buses and transmission lines. This power is supplied by generators at generating buses, and this flows of active and reactive power is so called load flow or power flow. Now in any system, we need to understand what are the parameters which are commonly available to us, either voltage magnitude, phase angle at each bus, power flow in each system branch, power injected at each generation, and system losses. So the main objective of load flow is to determine voltage at each bus, phase angle at each bus, power flow in each line or branch, power injected at each generation sources, as well as the total system loss of the network need to be identified. Now when you talk about conventional power flow methods, there are many variety of load flow analysis systems or different type of algorithms, popularly known as Gauss-Seidel, Newton-Raphson, fast decoupled methods, and which are commonly used for transmission system. However, there are bit of challenges, so called the traditional Gauss-Seidel method and Newton-Raphson method need the calculation of the Y-bus matrix as well as Jacobian matrix. And when solving large power system, the most difficult computation, which is basically the Y matrix and the Jacobian matrix and their inversion. Inverting a full matrix need an order of n operation, which is of inverting a full matrix need an order of n to the power 3 operation, meaning the amount of computation increases with the cube of the bus size n. Now quickly getting into Newton-Raphson method. The Newton-Raphson method, which is an iterative technique for solving a set of various nonlinear equations with an equal number of unknowns. As you all know, S, the apparent power, which is P plus JQ, and the value of P at a particular bus I, injected real power and injected reactive power at bus number I is given by the equation 15.2 and 15.3, which is very standard. But now we'll concentrate how these equations do pose a challenge before the distribution network load flow analysis. Now in case of Newton-Raphson, we determine the Jacobian matrix, which need to be constructed by partially differentiating equation number 12, 15.2 and 15.3 with respect to delta and V. So what will happen? We'll have actually dou Pi upon dou delta I, and we'll have dou Pi upon dou Bi, similarly dou Qi upon dou delta I and dou Qi upon dou Bi. So that means both P and I, which has been partially differentiated with respect to delta I and Vi. Now what is happening, once the Jacobian matrix is available to me, we multiply it by the correction matrix, which is delta delta I as well as delta Vi upon Vi, which is equal to a mismatch matrix, that is delta Pi and delta Qi. The convergence of Newton-Raphson method depend on the following, that is diagonal dominance, sparsity, and well-conditioned or ill-conditioned matrix. Now when you talk about sparsity, we need to know what is sparsity first. In distribution network load flow studies, sparsity means that the network matrices such as the admittance or impedance matrices contain mostly zero entries or elements. In a distribution network, the bus admittance matrix, Y bus matrix, and Jacobian matrix used in Newton-Raphson method are often sparse, meaning they contain a large number of zero elements in that matrix. This is due to the fact that in a radial or weakly meshed network, each bus is directly connected only to few other buses, so most pairs of buses have no direct electrical connections. As you know, if it is going to be radial, that the buses of one radial system to the other radial system or one radial branch to the other radial branch, they are not connected. That means my matrix, most of the elements, if 1 and 3 is not connected, then probably Y1, 3 will be my zero or sparse. This can cause the Jacobian matrix can become a singular, non-invertible, causing convergence problems. Now, if you are interested to know what is sparsity in terms of percentage, the number of zero element divided by total number of elements of a matrix multiplied by 100 will give you the percentage of sparsity a network carries. The sparsity in case of transmission system is slightly less. However, in case of distribution system, because they are radial and not connected, and hence the sparsity becomes significantly high in case of distribution systems. So, inverting a Y matrix or a Jacobian matrix in case of a distribution system become quite challenging. So, we will explore different methods for carrying out load flow studies for distribution system instead of simply getting into Newton-Raphson load flow algorithm. So, most of the researchers across the world have used modified Newton-Raphson algorithm for distribution load flow, or they have gone for a unique method of load flow algorithm or load flow solution studies. In our analysis, we will try to propose a new algorithm, especially graph-based load flow solutions for distribution system in detail. Now, let us consider a 4-bus transmission system. As you could see, this is 1, 2, 3, 4. And the data for the 4-bus system is given to us, all the bus data, and we do have the line data. And with a base value of 230 kV and a base value of 100 MVA, with these two base values, if you want to form a Jacobian matrix, the Jacobian matrix after first iteration for a 4-bus transmission system look like this. As you could clearly see, there are a couple of zeros. You could see, and most of them are actually negative as well as positive mix. That is no problem. But the worrying part is the diagonal is too dominating, which is order of close to 50, and others are either actually 5, 10 or single digit numbers. Now, the number of zeros in this case, if you count very closely, so there seems to be 1, 2, 3, 4, 5, 6, 7, 8, and total we have actually 4 by 4, there are actually 16 elements. So, the Jacobian matrix after first iteration for a 4-bus system can be obtained, and you can see that it is going to be a 5 by 5 matrix. So, the total elements are going to be 25 and the sparse elements are going to be 8. So, the sparsity can be calculated as 0.8 divided by 25 into 100. So, approximately 32% of elements of the Jacobian matrix of a 4-bus simple transmission system is 32%. Now, similarly, if you move for a 17-bus weakly meshed distribution network, and we can once again calculate the Jacobian matrix of the same network, as you could see, and you can find there are 808 elements are 0 out of 1024. That means approximately 80% of elements of the Jacobian matrix is sparse. That means in the first row, sum of the absolute value of off-diagonal elements is 2045, which is greater than the diagonal value, that is 580. So, it is very critical to inverse such matrix, and perhaps most of the cases the inversion is not possible due to serious sparsity within the matrix. Now, this is another system where it is 17-bus radial distribution network, and we can once again determine the radiality. Here we could find there are 848 elements are sparse out of 1024. So, approximately 82% of the elements are going to be 0. Now, let us try to understand what is well conditioned or ill conditioned system. Now, condition number defines the condition of Jacobian matrix with respect to the computing problem, that is k of j, which is given by lambda max upon lambda mean, where lambda max is the maximum eigenvalue and lambda mean is the minimum eigenvalue. Ideal value of conditional number should be 1 for a well-conditioned system. Now, well-conditioned or ill-conditioned system, if you determine type of system, if number of buses are going to be 30, maximum eigenvalue is 108, minimum is 0.2, the condition is 468, and this is going to be moderately well-conditioned. Similarly, we can go to bus number 11, maximum eigenvalue 122, minimum eigenvalue 0.11, the condition number is going to be 1086, so it is ill-conditioned because it is too high. And similarly, if you go for bus number 13, we get 2014. If you go for bus number 43, we are getting actually 25,600. So generally what we can argue that if the condition number, if it is significantly high, then it is ill-conditioned and which is not good actually, it is bad for the system. However, a high condition number for the matrix J indicates that the system is ill-conditioned. More value for your condition number leading to ill-conditioned, meaning that the computed results are highly sensitive to even small change in the input value. That means the calculated parameters are quite sensitive with respect to the small change in my initial values. Now, if you go for convergence characteristic of different methods, we can consider actually again the same set of case studies, bus with 11, 13, 43, 14 as well as 30 and 57, and we could see Gauss-Seidel which is divergent and Newton-Raphson which is equally divergent, fast decoupled divergent. So, for any ill-conditioned system you could see the system is not converging properly. However, if it is well-conditioned system, I think we could see that with number of iterations the system become convergent. The Newton-Raphson load flow approach is divergent in the case of ill-conditioned system, and that demonstrate that it is always better to have a well-conditioned system instead of ill-conditioned systems. Now, what are the challenges with conventional system? In power flow solutions that requires inverting the matrix, loss of diagonal dominance in the Y bus or Jacobian leads to convergence problems. Okay, so what we have understood that if your Jacobian matrix is having lot many zeros, or if the matrix is going to be a sparse matrix, then certainly the inversion is difficult, and which is a common requirement in my load flow analysis. So, as shown previously, okay, a radial or weakly meshed distribution network, Jacobian matrices are typically sparse, containing many zero elements. An ill-conditioned Jacobian in the network or any system where we apply Newton-Raphson method is signaled by a very high condition number. A very high condition number indicates that the system is ill-conditioned. Its computed value are extremely sensitive to small change in the inputs. As shown previously, radial or weakly meshed distribution networks are ill-conditioned systems, and hence traditional power flow methods are not preferred or acceptable. So, most of the distribution systems today are actually ill-conditioned because the condition number is quite high, and if the condition number is quite high, that means the Jacobian inversion is quite difficult. With this note, we stop today's lecture. Thank you very much.